Hi class! In this video we are going to take a look at the types of arrows that we can use in our acid-base reactions in order to indicate which side of that reaction is favored. Is it product favored or is it reactant favored? We're going to use some of the things that we've discussed throughout this foundational review, things like our ARIO rules, so atom, resonance, induction, and orbital, as well as pKa. Okay, so sometimes you'll need one or the other, and you can use both to confirm. And the takeaway from this, though, is that the equilibrium favors the weaker acid, weaker base. Okay, so all we have to do is identify the weaker acid or the weaker base, and we know what side is favored, right? The weaker acid and weaker base will always be on the same side of the reaction equation if you've done it right, and we will know that the equilibrium favors the weaker species based on our ARIO rules or pKa. So let's take a look at this reaction with ammonia and HCl that we drew out before. So we know that ammonia is going to take the proton from HCl. This is the acid. This is the base, right? So we're going to compare the acids on either side. So my conjugate acid and my acid. So using our criteria, these aren't quite the same. So we're talking about HCl, which is a neutral molecule, and NH4+, which is charged. So you have to make sure that when you're making these comparisons, you're comparing apples to apples, and you're not comparing apples and oranges. So to use the ARIO rules directly is not going to work out here, okay? Now, some intuition will tell me that HCl is a strong acid, and ammonia here is a weak base, so that is going to produce a product-favored reaction here. So anyway, though, we can use pKa to justify this. This is -8, and then the pKa of the ammonium ion is around 9. If we're going to use pKa to justify our arrow choice here, there's some guidelines that I want to lay out for you. If our difference in pKa is less than 2 units, we're going to use a true equilibrium arrow. And so remember that pKa is equal to the negative log of the Ka. And so since this is a log scale, 2 pKa units is going to be 2 orders of magnitude, or 10 times 10, or 100 times. So if the difference is less than 2, we're talking about less than 100 times more of a product or reactant, and we're going to essentially say that this is in equilibrium. Now, if our difference in pKa is between 2 and 5, then we're going to say that it's a lopsided arrow, either favoring the products or favoring the reactants, okay? And if it's greater than 5, that means it's 5 orders of magnitude or more than 100,000 times favoring the products or reactants. We're going to use a one-sided arrow. So for these types of reactions, we're basically going to have 5 choices for our arrow, and we're going to base that on our pKa differences. If we don't have the exact pKa values, we can kind of estimate, and sometimes I won't ask you specifically for the arrow, just whether or not a reaction is product favored or reactant favored. So given that the difference in pKa, -8 to 9, is 17 units, that would be greater than 5, and we're going to have a one-sided arrow here. And the arrow that we choose is going to point towards the weaker acid-base pair. So since the pKa is -8 and this is 9, the higher the pKa, the weaker the acid. So this acid is weaker than HCl, and therefore Cl- is weaker than ammonia. So this is going to be a product favored. This will go essentially 100%, right? There's 10 to the 17th times more product than reactants. So there's a negligible amount of ammonia and molecular HCl in the solution. Let's try a few more for practice. Feel free to pause the video at this time and take a minute to figure out the acid and base in this reaction and to draw out the products. So in order to figure this out, we're going to look at our ARIO rules or pKa. So if we look at this, we're going to find OH bonds. So the atom is the same. And then we're going to go on to resonance. So is there resonance in the conjugate base of either of these species? So I'm going to draw the conjugate base just so I can see it more clearly. And see if I can push electrons around. So of course in the acetate ion I have that resonance, and then in the phenolate ion I can push electrons around this ring to generate contributors that look like this. And of course this pair of electrons can get pushed around the ring to form two more resonance structures. And I encourage you to draw those out for practice, okay? And then how do we figure this out? Well, okay, we both have resonance. Then we could go to inductive effects. Well, it's hard to know here because there's alkyl groups on each side here. So then we might want to go to our pKa chart. And once you practice using your pKa chart enough, you'll become familiar with the ballpark ranges for these particular acids. And I will ask that you know these pKa's at some point. So pKa for acetic acid is around 5. So any carboxylic acid is going to be about 5, okay, with slight variation depending on what groups are attached out here. Then phenol, parent compound, is around 10. All right? So now we know that the stronger acid is acetic acid and the weaker acid is phenol. So the conjugate base here, the conjugate acid will be the protonated phenol, and then the conjugate base will be the carboxylate. Okay, so conjugate acid, conjugate base. All right, so this is my acid, this is my base. So drawing the mechanism, we are taking this proton and leaving behind that. All right, so then we're going to compare the conjugate acid to the acid. So pKa is 5 here, and then we're looking at a protonated oxygen with a positive charge. So thinking about our pKa chart, this is going to be a negative pKa, right? Protonated alcohols are on the order of negative 2.4. This is going to have electron withdrawing benzene rings, so it's probably going to be a little bit lower than that, but a negative 2.4 is a good ballpark estimate for us, and it's suitable enough for us to choose an arrow here. So 5 compared to negative 2.4 is 7.4 in terms of its difference, and this will favor the weaker acid, which is 5 compared to 2.4. This one's no longer relevant since it's functioning as a base, and would be 100% reactant favored. And so what does that tell me? If I want to protonate phenol in this way, would I choose acetic acid as an acid to do this? No, because we're going to have 10 to the 7th times more reactants at equilibrium, according to the difference in pKa. So this allows us to choose appropriate acids or bases to carry out the things that we want them to do. Now this is just a guide, and it will vary from person to person as far as what the criteria is. There are some exceptions to this, and those are being the strong acids. So we know that anytime a strong acid like HCl, HBr, or HI are mixed with water, we will get 100% dissociation into the hydronium ion and the conjugate base. And so most of the time when we're using strong acids in our reactions, our source of protons is going to be the hydronium ion. Same thing with sulfuric acid. In water, it loses 1 proton to form HSO4 minus and hydronium ion. So anytime we see these acids in our chemical reactions, we will be wanting to use water as the hydronium ion as our proton shuttle. And if you look at the pKa's here, negative 5 and negative 1.7, you'll find that the difference is less than 5, and so that would be within this 2 to 5 range, but we're going to to look at this as 100% dissociation because they are strong electrolytes. We know that they dissociate into ions, and so that's where this kind of breaks down, is with the strong acids. And this will also be the case if we swap out water for an alcohol. So say we're going to put HBr in ethanol, and we would produce Br minus and the conjugate acid of ethanol. We'll say that this is a one-sided arrow here. And this will come up in some of the reactions that we do as well. So keep in mind that strong acids in water or alcoholic solvents will completely dissociate. This will be the last example that we work together. So I want you to take a second and look at these two compounds, predict the products of this acid-base reaction, and then think about which side would be favored. So in looking at this, you can tell that OH minus would function as the base here, and the carbonyl would function as the acid. And in which case, we have to find the protons. They're hidden there on the ends of the carbon chain. It doesn't matter which side we take them from. That'll be the same. And so we end up with a carbanion and water here. So this is my conjugate acid and my conjugate base here. The acid, in terms of pKa's, or using our rules, we're comparing these two species. So hydrogen attached to oxygen, hydrogen attached to carbon. Which is the stronger acid? Well, carbon and oxygen are in the same row of the periodic table, so the more electronegative element is going to be the stronger acid, and so this acid would be stronger based on those rules. And if we look at the pKa of water is 15.7, and the pKa alpha to a ketone is about 19. So they're close. And the reason why this carbon-hydrogen bond is much more acidic than a traditional carbon-hydrogen bond is because of the resonance present in the conjugate base. So you can draw out the resonance contributor here and see what that looks like. Sharing the charge brings stability, making it a weaker base. So then we can think about the favorability in the arrow that we're going to take. So 15.7 to 19 is just over 2, and we favor the weaker acid, weaker base pair, which happens to be the reactant side. So we're going to have a lopsided arrow favoring the reactants, indicating that there will be more reactants present at equilibrium than products. But that's okay, because Le Chatelier's principle will work in our favor if we want to do this in a chemical reaction. So say we want to produce this carbanion. This is a form of an enolate, and you'll use this in Chem 212. But this can function as a nucleophile, and as this is consumed through another reaction, that's going to shift this equilibrium to produce more product. So it's okay that it's reactant favored. Just as long as some product is produced, we can start to siphon that off as it's consumed. Practice doing this with some example problems in Canvas, and reach out if you have any questions. Thanks for watching.